Okay, so let's discuss depth first search now. Depth first search is a special instance of the Explore algorithm we talked about before. And specifically, let's start off with depth first search in undirected graphs. Okay, so depth first search is a special case of basic search and is very useful in understanding graph structure. And you could use depth first search to obtain linear time algorithms for finding cut edges and cut vertices in undirected graphs. A cut edge or cut vertex is a edge or vertex that divides a undirected graph. Or you could use it to find the strongly connected components of directed graphs, as we'll discuss here, as we'll discuss in later sections, but in this lecture. And there's just a myriad of applications there as well. So let's discuss depth first search. And let's start off with the depth first search algorithm, which is almost exactly the same as a basic search algorithm. We've simply made it slightly simpler, simpler here. And so depth first search, it can be written as a recursive algorithm, and the beauty of this, the beauty of the way it's written here is that while you don't have any data structures to store the particular vertices, that you need to visit next. Remember that that structure that data structure that you had named to explore, that simply stored the vertices that you needed to explore. In this case, the depth first search simply recurses on itself. It recurses on itself by calling depth first search on the adjacent vertices. Okay, so this is the equivalent of if the basic search algorithm was written with the to explore data structure as a stack. Okay, in this case it's exactly the same, except it's using the program stack, the stack that's part of the OS that handles function calls. It's using that stack instead of a actual physical stack. Okay, but all that first search does is simply, given a graph G, assuming it gets a vertex U, it marks U as visited, and then for each edge going out of U, if that vertex has not been visited yet, then it adds that edge, then it marks that edge for a tree. We'll discuss the tree in a moment. It sets the predecessor of this vertex U, or it starts the predecessor of the adjacent node as this vertex U, and then it calls depth first search on the adjacent vertices. Okay, so sometimes it is useful to store the edges that depth first search traverses to find a new node as a tree. Okay, and it could have this could be used for a myriad of other algorithms, many of which we'll get into momentarily. So let's go through a particular example. And you have a tree edge that belongs to T, and this is cut off, and you have non-tree edges that don't belong to T. Pretty simple. To T. So in this graph here, you have a particular tree highlighted as the dark edges. Namely, you started a DFS on vertex 1, then you looked at the adjacent vertices, and you look at the adjacent vertices and see vertex 2. So you make another function called toDFS for vertex 2, and you mark this edge as the edge you took to get to vertex 2. And you say vertex 2's predecessor is vertex 1. That's if we need the traversal path later on. That's how we could get it. Then at vertex 2, it has a bunch of adjacent vertices, but if simply we call DFS on the first one, vertex 4, and then we go into vertex 4 right away. Okay, so depth first search is a first in last out algorithm. Okay, what the depth first search is doing is simply when it reaches a particular vertex, it sees that that vertex has a bunch of adjacent vertices, but it simply finds an adjacent vertex that hasn't been visited, calls itself, and then in the new function call you explore further. And if there's nothing to explore further, such as 5, you made a DFS call to 6, but 6 you can't do anything else, so that this chain of the recursion fizzles out. You go back up to 5, and then 5 looks for another adjacent vertex. It finds 3, and then you visit 3, and then you visit 7. It looks, and then when the DFS call for 7 looks around for adjacent vertices, sees 8, calls DFS 8, and 8 fizzles out, because while 8 is adjacent to 3, 3 has been visited already. Okay, like so. And there is a little bit of wrapper on this function that says if if you do make the DFS call and then you come back and you have vertices that are still unvisited, then it will call those vertices as well. And that's helpful in the case of this graph, because the graph itself is, while it's undirected, it's not connected, because you have more than one connected component. Okay, so let's go through just a fine grain. So we will go through a fine grain example of DFS with this graph also, but there's one other statistic that we should keep track of with DFS, not just the DFS tree, not just the DFS path that we take with the predecessor list, but there is one other characteristic which is incredibly useful, which is known as pre-post numbering. Okay, so what is this characteristic? Well, let's say that as we're doing the DFS calculation, we also keep track of the time that we spend at a particular vertex. We keep track of the time that particular vertex is active, i.e. the time that the children or the children's children or the children's children's children of that vertex are continue to be explored. We want to keep track of that time. So in order to keep track of that time, we could simply have a pre-counter, we could simply have a pre-counter which denotes the first time that this particular vertex is entered, and we have a post counter which denotes the time when all the vertices adjacent to this vertex have been explored, and therefore the recursion on this vertex has finally ended. Okay, so I know it seems a little odd. Why are we keeping track of the these pre and post numbers? I promise you it will make more sense in the coming lectures. But let's for the moment keep track of these things. Do an example where we keep track of these things. So let's say at time equals 0, we have this graph, and we have no vertices explored yet, and no pre-post numbering. Okay. So what do? We simply enter vertex 1. Okay, and this yellow ring means vertex 1 is active. So vertex 1 has been explored. It's part of our DFS tree now, and we know the pre-numbering for vertex 1 is at time 1. Then what do? We look, depth first search looks at adjacency vertices and calls DFS on 2, right? So next point, it finds 2 and then calls DFS on 2, and it enters DFS2 at time 2. So that's our pre-numbering for 2. And 2 is still active and 1 is still active. 1 is still active because the children of 1 and their children's and so on are still being explored. The only time 1 will stop being active is when all its children stop going inactive and the recursion comes back onto it and ends. Okay? So same deal. 2 looks at the edges coming out of it, and it finds 4, so it explores 4 next. 4 is assigned a pre-number, and then so on and so forth. We explore 4, then 5, then 6. Now, we reach 6 at time 5, okay? We reach 6 at time 5, and then we go through the DFS logic and see, oh, there's no more unvisited adjacent vertices to explore. So DFS coming out of 6, it's over. It doesn't need to know. It doesn't need to do anything anymore. So what do is that we assign a post number to 6. So 6 ceases to be active at time 6. It deactivates. And now 5 is still active, so 5 can continue with the DFS and look at if there are any other adjacent nodes that have not been visited yet. And of course there's 3. So 3 is assigned a pre-number at time 7, and then 3 finds 7, and then 7 finds 8. And of course we reach 8, and again, there are no more adjacent vertices to go to. So 8 has to stop being active, and so its post number is time 10. Then 7 has no more adjacent vertices to visit, so 7 stops being active, and then we assign a post number of 11. 3 stops being active, no more adjacent vertices, no more unvisited adjacent vertices, so 3 stops being active, so it deactivates at time 12, and so on. And of course, we get the DFS starting at vertex 1, but our wrapper function for DFS also said that if there are still unvisited vertices, then to do a DFS call on those unvisited vertices. So DFS is called on vertex 9, which is still active. Then it's called on vertex 10, pre-numbered at time 18. Then 10 deactivates, then 9 deactivates. And therefore, we have the pre-post numbering for these vertices. We did DFS. We have the DFS tree, basically the edges the DFS took to find all the vertices. We also have the DFS predecessor, the path DFS took. We have the tree, and we have the path DFS took to find all the vertices. Next, and finally, we have the pre-post numbering. When these vertices were found and at what time, and how long it took to find all the children and the children's children of those vertices. And so we could lay out these pre-post numbers in an interval graph, like so. And immediately what we see is that the intervals always encompass, larger intervals always encompass smaller intervals. Okay? So that's an important point. As you saw when we went through the example, the pre-post numbering, the larger intervals always encompass smaller intervals. The larger intervals correspond to vertices that were found before their children along the path. Okay, so the pre-post numbering gives us a node U and says that it's active during the time interval pre of U and post of U. And one important thing to realize is that for any two nodes, U and V, the two intervals are either completely disjoint or one is contained in the other. Okay, so important part there. So that is pre-post numbering. In a moment, we're gonna use pre-post numbering to do all sorts of interesting algorithms. So stay tuned.